Welcome back to The Explainer. Okay, today we are embarking on a really exciting deep dive into an open source project that is quietly powering some of the most advanced language models in the world. We're talking about Slime. This is an LLM post-training framework that is absolutely fundamentally revolutionizing how developers handle reinforcement learning, or RL scaling. Now, if you've been following all these massive leaps in model reasoning and agentic behaviors recently, well, the secret sauce behind that is RL post-training. But the underlying infrastructure to actually do that at scale, historically, it's been an absolute nightmare.
Okay, let's dive right into this. Because honestly, the core problem in this space is just pain. If you are building frontier models, scaling reinforcement learning is notoriously difficult and highly prone to silent bugs. And you might be wondering, why is that? Well, it's because developers usually end up having to cobble together this bloated, heavy stack of completely disconnected multi-backend trainers, standalone rollout services, and messy agent frameworks. You've got one system trying to generate data, you've got another trying to compute rewards, and a completely different engine trying to sync the weights. It's fragile, it breaks, and worst of all, it fails silently.
So, to escape this infrastructure trap, we're going to explore 5 key areas today. First, we'll meet the Slime framework itself. Second, we'll look at its pass-through design. Third, we'll peek inside Slime's architecture. Fourth, we'll see how it's battle-tested. And finally, we'll explore the wider Slime ecosystem.
Let's start with Section 1. Meet the Slime framework, an antidote to the bloated stack.
Slime is essentially the direct antidote to that disconnected Frankenstein tech stack that plagues AI labs trying to scale their post-training. Basically, it's an LLM post-training framework built specifically from the ground up for RL scaling. The way it works is by seamlessly connecting Megatron, which, handles all the high-performance training, with SGLang, which handles flexible, high-throughput data generation. So, the absolutely crucial takeaway here is that Slime is an opinionated framework. It enforces a very specific design where training and rollout actually reinforce each other, rather than acting as these disjointed, battling systems. Literally everything, custom data generation, reward computation, verifier feedback, it all flows through one unified path.
I really want to highlight this specific quote straight from their engineering documentation. It says, "RL bugs are often silent." Man, this is such a profound truth in AI development. Just because a script runs without crashing doesn't mean the model's actually learning correctly, right? Because of this terrifying reality, Slime is built as a correctness-first infrastructure. It keeps the data flow totally explicit. It supports completely separate debug paths if you want to just test rollouts or just test training. And it treats reproducibility, fault tolerance, tracing, profiling, and CI as first-class engineering concerns. No more guessing if it's actually working.
Moving right along to Section 2, the pass-through design, letting engines speak natively. So, there is a massive difference in design paradigms happening here. Most multi-backend frameworks out there try to support literally every inference engine under the sun, and the result, well, they abstract over the common subset of all of them. They create this lowest common denominator wrapper that actually ends up hiding the strongest, most unique features of each individual backend. Slime takes the exact opposite approach. Like we said, it's deeply opinionated. It relies on a native pass-through directly to SGLang and Megatron. It isn't throwing a thick, confusing blanket over them. It actually lets the engine speak natively.
So, what exactly do you gain by this native design? A whole lot, actually. Because of this pass-through architecture, any argument that is supported by SGLang works instantly in Slime. You literally just add a --SGLang prefix. Boom, you're done. Megatron's wildly complex parallelism, optimizers, and checkpointing configs, they stay native. No clunky translation wrappers needed. But the real magic happens in those RL-specific workloads. You get native prefill/decode or PD disaggregation. I know that's a mouthful, but it is absolutely vital for multi-turn agentic workloads that have vastly different resource needs. You also get delta weight sync. This enables super efficient updates for massive models across disaggregated training and inference setups. Basically, whenever there are upstream improvements in these engines, they are immediately accessible to you, no waiting for a framework update.
Let's look under the hood in Section 3, inside Slime's architecture, the nervous system.
Let's move through and see how this builds a complete, highly efficient loop. Think of it like a nervous system with 3 core modules operating in total unison. First up, you have training. This is handled by Megatron, which reads from the buffer and syncs those updated parameters. Second, right in the middle, you have the data buffer. This acts as the critical bridge. It manages the prompt initialization, the custom data, and the routing. And third, you've got the rollout module, which is powered by SGLang and a router. This part actually generates the new data, computes the rewards, and feeds it all right back into the data buffer. It is clean, it is cyclical, and it entirely eliminates that heavy, messy stack of spaghetti code we talked about earlier.
Which brings us to Section 4, battle-tested in production, validated by frontier models.
Now, it is one thing to have an elegant architecture sketched out on paper. It is a completely different ballgame to survive the brutal realities of release-grade model training. If you jump over to the Slime GitHub repository, you're going to see over 6,500 stars. And look, that number isn't just some vanity metric. It visually punctuates the massive scale of community trust and widespread adoption this framework has already achieved. It's somehow small enough to actually understand and extend yourself, but robust enough to handle the absolute heaviest workloads imaginable.
Seriously, just look at the frontier models that validate Slime's full post-training loop in real, state-of-the-art production environments right now. We are talking about the entire GLM family, from 4.5 all the way up to the latest GLM 5.2. It supports the massive Kuon series, including Qwen 2.5 and the bleeding-edge Qwen 3 MOE. It is powering the globally recognized DeepSeek V3 series, including DeepSeek R1. And of course, it supports Llama 3. This framework is exercising the complete workflow: the large-scale training, the high-throughput rollout, the weight synchronization, the long-running stability, for literally the most important, heavy-hitting models in the world.
Finally, let's wrap up with Section 5, the Slime ecosystem, limitless versatility. Because Slime doesn't stubbornly fork the training kernel, it serves as an incredibly versatile, totally reusable RL substrate that extends far, far beyond just standard text generation. To show you exactly what I mean, let's do a rapid-fire look at some of the independent systems built entirely on top of Slime. You have a project called Miles, which pushes enterprise-grade, large-scale model training with serious operational tooling. Then there's Relax, which is achieving omnimodal agentic RL, we're talking text, vision, and audio, over an asynchronous service-oriented architecture. There's Triton Forge, leveraging Slime's RL to automatically train LLMs to generate high-performance PyTorch GPU kernels, and Art, which provides scalable, sandboxed agentic RL directly on the AWS Bedrock runtime. The sheer versatility here is just astounding.
But what's really fascinating to me is seeing how Slime jumps off the server and into the physical world. Check out OpenClaw RL. This is a system for training personalized physical robotics, specifically clawbots. It works by having the RL server host the model and actually improve its real-world physical policy based on prior conversations across different deployments. And thanks to Slime's asynchronous infrastructure, the intense RL training happens quietly in the background without ever interfering with the live API that's serving the robot. It can literally extract hindsight hints from later feedback to optimize what the robot does. So cool! Then there is a project called P1. This is a family of open-source physics reasoning models trained entirely through reinforcement learning on the Slime framework. It uses this really clever multi-stage RL algorithm that progressively enhances the model's reasoning ability over time. It dynamically adjusts its learnability and stabilization to achieve genuine breakthrough performance in solving intensely complex, open-source physics Olympiad problems. And if you want to talk about sheer scale, we have to talk about a project called RLVE. RLVE introduces procedural verifiable environments to radically scale up RL for language models. Listen to this. It conducts joint training across 400 adaptive, verifiable environments simultaneously. 400! And these environments dynamically adapt their problem difficulty on the fly to match exactly what the policy model is capable of at that exact moment in training. It's an incredibly sophisticated dance of difficulty and capability, and it is all routed seamlessly, cleanly through Slime's data buffer. So by totally solving the massive headaches of multi-backend infrastructure, the parameter syncing, and those frustratingly decoupled workflows, Slime frees up developers to focus purely on what matters: the data and the rewards. The core training loop is finally solved. So, I want to leave you with this question to think about. What domain will you scale with verifiable environments now that the underlying RL infrastructure is waiting, ready for you? I highly encourage you to go check out their GitHub repository and see what you can build. Thank you so much for joining me on this deep dive, and I will see you on the next explainer.